Hello everyone, and welcome back. Last time we were looking at oscillations, like a mass on a spring, as a simple example. Today we're going to start looking at a different kind of oscillatory behavior, but with a more complex system. This brings us to section 15, waves. Last time we were looking at a mass on a spring as an example of simple harmonic motion. And when we displaced the mass and released it, it would oscillate up and down and up and down. Okay, but now let's imagine we've got a more complicated system that looks like this. Rather than a single mass on a single spring, let's imagine that we have a whole series of masses. Each mass attached to an immovable surface at the top, say, with a spring, but then each mass connected to the neighboring masses with springs in between. If we displace this mass and release it, what's going to happen? Well, this one's going to start to oscillate up and down, but then what? Well, because of the connection to the next mass, the motion of this mass will start this mass moving. And then the motion of this mass will start this mass moving, which will start this mass moving, etc., etc., etc. The motion will move down through the system. This is a very interesting result. This motion through the system is what we call a wave. I want to emphasize that there is no mass that is moving from here and going down the wave. Material itself is not moving in that direction. What's moving? Well, an oscillation is moving, or a perturbation, you might say. The disturbance is moving through the material from one end to the other. So that's very interesting. But let's notice, say, if we start out, that mass down there is not moving. If I start moving this one, then this one moves, this one, then this one, this one, this one, this one. Eventually this mass starts moving, and it starts having some kinetic energy. Initially stationary, it starts moving up and down. So what is moving down in that direction in addition to just the disturbance? Energy. So energy is moving through the material, the system. When we have a wave moving through something, we'll call this the medium. So waves flow or propagate or move through a medium. It doesn't have to be a physical medium like this, something solid. It could be an electric and magnetic field. That kind of wave is an electromagnetic wave. But there is something through which the wave moves. We'll stick with solid or some kind of material medium just for the time being. Okay, so what's important? This oscillation moves through the medium, and energy travels along with it. Okay, great. Now I'd like to distinguish just between two general types of waves. There are other ways that things can move, but there are a couple I just want to point out. How can we move this mass that would make a wave propagate through the medium? Well, as I said, I could move it up and down like this, and that up and down motion would then propagate through the medium. In other words, a motion up and down then propagates through the medium like this. So this is the direction of the velocity. In this case, the disturbance or the oscillation is perpendicular to the direction of motion of the wave. When the disturbance is perpendicular to the motion of the wave, we call this a transverse. A transverse wave. That end doesn't look so good. A transverse wave. Transverse, the perturbation is perpendicular to the direction of motion. Another way I could do it is if I were to move this mass forward and back. So when I moved it forward, it pushed this mass forward. When I moved it back, it pulled this mass back. And so by moving it forward and back, I would end up propagating a wave where the motion was actually in this direction, back and forth. So in that case, I would have an oscillation in this direction while the velocity is in that direction. So in this case, the perturbation would be in the direction of the velocity or opposite the direction of the velocity, back and forth. This type of wave is called a longitudinal. A longitudinal wave. Okay, great. It doesn't matter whether we have a transverse or a longitudinal wave, we can graph them to analyze what it looks like in the same way. Let's just think about that for a second. If we have a wave that's going up and down and up and down, we could actually graph on the vertical axis the actual position of the mass in the up and down direction. We might measure this as the y-axis. So if we measured y as being measured vertically, positive y being upward relative to the equilibrium position, negative y being downward relative to the equilibrium position, then we could have this y value and graph that. What is the position of these waves, or what do these masses look like? We could graph this as up and down and up and down. Now I'm going to graph a particular kind of wave with a very nice sinusoidal wave shape like that. Well, we'll come back to that in just a second. But that's one way of graphing it. If we had a transverse wave in this case, say forward and back, what would we end up with? We would end up with some regions where the masses were kind of clumped together. The density of the masses would be higher than the undisturbed density of the masses. So in that case, rather than position, we might graph something like density. The density of the masses. Now, obviously, I'm kind of making a little approximation here. We have individual masses at particular points. It's not a continuous medium, but hopefully you can imagine how we might extend this to a continuous medium where we had a whole bunch of masses very, very close together. We would end up with a similar sort of situation. But anyways, when the masses are then clumped together, the density would be higher than the average density, so we might have a positive variation in the density. When they were stretched out, we might have a lower density of the masses, so that it was lower than normal, and then we might have a negative value for the density. So either way, graphing the transverse wave or the longitudinal wave, we can graph them in a similar way with some y variable that might be the position, might be the density, might be something else for some different kind of wave motion. But then in the x direction, we actually are talking about what is the value of that particular wave as we move in space in the direction of the motion of the wave. Okay, great. What I'm going to do is just draw something like this again, and we're going to take a look at some of the characteristics of the wave from our graph. So, we can graph our wave, whether it's transverse or longitudinal. We can get some sort of similar way of graphing it. Depending on how we actually move the mass to begin with, that will change the shape of the wave. We might move the mass with a very irregular kind of motion, up and down, or we might move it forward and back with a very irregular motion, and we'll get a very irregular shaped wave. If, however, we move the mass in a nice sinusoidal fashion, either up or down, or we move it back and forth sinusoidally, we'll end up with a nice sinusoidal looking graph. And this particular kind of wave is called an harmonic wave. Okay, so we'll assume that we've got a nice sinusoidally shaped wave that looks something like this. There are some characteristics here I want to talk about. First, if we pick two consecutive similar points on the wave. Now, what do I mean by that? Well, let's imagine, let me just mention, so the maximum points here, maximum, let me write that. The maximum points on the wave are referred to as the crests or the peaks. The minimum points down here, minimum, are the troughs or valleys, either one. The distance, say, between two consecutive peaks or two consecutive troughs, the distance between those points, the physical distance, or really between any two consecutive similar points. So imagine we pick a point here. So this value for y as the wave is going up and we come over here and find a similar point, same value of y as the wave is going up, the distance between those 2 points, they'll be the same as long as we have a harmonic wave. This distance we call lambda, where lambda is the wavelength. We call that distance the wavelength of the wave. It tells us how long in space, what's the distance that is covered by one complete oscillation. So when we talk about the wave making one complete distance of wavelength, we mean one complete oscillation. And it could be, say, from equilibrium to equilibrium going up, not just equilibrium to equilibrium, that would be half of a wave. So going up from equilibrium to going up from equilibrium across equilibrium, that would be one wave, or here to here, one wave, here to here, one wave. That would be one oscillation or one wave. I'll refer to that in that way. The distance of that, the length of that, we refer to as the wavelength, lambda. This is a lowercase Greek letter lambda. The units of lambda, because it is just a distance, the standard SI units that we'll use are meters. Then, the size of the wave, we might say, in other words, the distance from equilibrium to the maximum point. Now, I say distance, but it doesn't necessarily have to be exactly a distance. If this were measurements of, say, the density of the masses in a longitudinal wave with the masses on a spring, this could be a variation in density, a change in density or something like that. So whatever the type of wave you're graphing, whatever you are graphing on y, whatever that quantity is, the difference from equilibrium to the maximum point, we'll refer to this as the amplitude of the wave, and we'll represent that with a capital letter A. So this is the amplitude. Now be careful, the amplitude is not the total change of the wave from max to min. It's from maximum to equilibrium, and for a harmonic wave, it'll be the same as from equilibrium to the minimum value. So it's 1/2 this variation from max to min. So either equilibrium to the maximum value or equilibrium to the minimum value, that difference is the amplitude A. What are the units of A? Well, that will depend on what the units are in the y-axis. Could be density, could actually be a distance, meters, could be force units or whatever. Depends on what kind of wave it is. Okay, very, very good. Now, let's imagine what's going on. Remember, this wave is traveling through space. Let's imagine that we're standing over here and we are watching this wave pass us by. So we're over here and the wave is passing us by, and we count how many waves, and I mean how many complete waves, pass us every second. So we count these waves as they go by. 1, 2, 3, 4, 5. How many waves pass us per second? That is what we refer to as the wave frequency. Frequency is the number of waves that pass us per second. Frequency is a quantity that we've seen before. Hopefully, can you actually see that now? Let me put it over here. The number of waves per second. Frequency is a quantity we've seen before, in particular with oscillations, and it doesn't just mean waves per second, but frequency could be oscillations per second or anything that's repetitive. We could talk about the number of those things per some unit of time. For the standard SI unit, it will always be in terms of seconds. How many of those things, how many oscillations, how many waves, how many repetitive things are occurring per second. So this could be number of waves, could be number of oscillations per second, could be number of cycles per second. Whatever is cycling through multiple times. This unit, because it is used so often, has its own name. 1 cycle per second is called a hertz. And we write a capital H, lowercase z for short. So 1 hertz means 1 cycle per second. Okay, very, very good. Now, again, back to this person watching the wave. If you are standing right here, you'll notice that as the wave passes by, it will go down, and then it'll go up, and then it'll go down and go up. So, as a function of time, the displacement that you will see at your position will vary in time. Well, rather than graphing our wave as a function of position, let's graph our wave, the displacement variable y, but now as a function of t. So imagine that you're standing here, we're going to graph what the wave does for different values of t.